In this lesson, we'll consider the multivariate Gaussian hypothesis test for the special case when the means are equal, and we'll outline an approach for evaluating the corresponding receiver operating characteristic. Well, in our previous lesson, we showed that all multivariate Gaussian hypothesis tests can be pre-processed so that the data have zero mean and an identity covariance for hypothesis 0, and are uncorrelated with a diagonal covariance for hypothesis 1. Accordingly, we showed that the general form for the decision test looks like this, where m, again, is the number of elements in the observed data vector, n is the number of independent observations for the data vector, and the parameters mu and lambda are determined by the original means and covariances according to the pre-processing steps. Now, if the means are the same for both hypotheses, then the mean for the pre-processed data under hypothesis 1 will be 0, and all the values for mu will be equal to 0. This means that the second term in the decision statistic will be equal to 0, and the decision test then would look like this. Now, because the data are zero mean Gaussian for both hypotheses, and because the decision test is a quadratic function of the data, the resulting decision statistic will be a linear superposition of chi-squared random variables with n degrees of freedom for both hypotheses. Under hypothesis 0, for instance, the variances for all the data are equal to 1, so the sum of the squares over the realizations for each element of the observation will be a chi-squared random variable with n degrees of freedom, and the superposition will have the coefficients lambda m minus 1 divided by lambda m. Under hypothesis 1, each element of the pre-processed data will have a variance equal to the corresponding element of lambda. Accordingly, if we take the lambda term from the denominator of the coefficients and take that inside the sum, then the normalized observations will have unit variance, so that the normalized sum of the squares will also be a chi-square with n degrees of freedom, and now the superposition coefficients would be lambda m minus 1. Therefore, we can think of the decision statistic as a linear superposition of independent chi-squared random variables where the superposition coefficients depend on which hypothesis is true. When hypothesis 0 is true, the coefficients are the ratio of lambda m minus 1 to lambda m, and when hypothesis 1 is true, the coefficients are simply lambda m minus 1. To determine the false alarm and detection probabilities, then, the challenge is to evaluate the probability density for a linear superposition of chi-squared random variables. Now, whereas finding the density directly is difficult, we can evaluate the characteristic function for the random variable s in a rather straightforward way, where the characteristic function is defined as the expected value of e raised to the negative j times 2 times pi times the random variable s and a parameter nu. Now, this turns out to be an integral that looks exactly like a Fourier transform, where nu might be interpreted as a frequency variable. This means that determining the characteristic function is equivalent to determining the probability density, provided that we can evaluate the inverse Fourier transform. To do that, we can begin by evaluating the expected value of e to the negative j 2 pi nu. Now we'll replace s with the superposition of alpha m times the independent chi-squared random variables. Now, if we convert that summation in the exponent to a product of the exponentials, and then note that all of the random variables are independent and identically distributed, we can take the expectations inside the product, and again, because all of the random variables have the same distribution, those expectations are the characteristic function for the random variable w, but evaluated at nu times alpha m, which, because w is a chi-squared random variable with n degrees of freedom, will look like this. In this context, then, the decision test looks like this when the data are from hypothesis 0, where the coefficients are lambda m minus 1 over lambda m. Therefore, the characteristic function has this form, and if we can invert this Fourier transform, we can use this density to evaluate the false alarm probability. Likewise, the decision statistic looks like this, when hypothesis 1 is true, and the corresponding characteristic function looks like this. And if we invert this Fourier transform, we can use that density to evaluate the detection probability. Well, here, for example, are some plots that show the orientation and shape for some two-dimensional probability densities, Gaussian probability densities. In each plot, the blue ellipse corresponds to the density for hypothesis 0, which has the diagonal covariance we've shown here. And the density for hypothesis 1 is represented with a different color in each of the plots. And that density has the same eigenvalues, but is rotated by an orthonormal eigenvector matrix that looks like this, where there's a parameter theta. The upper right plot, for instance, corresponds to a rotation theta of pi over 8. The upper left is pi over 4. The lower left is 3 pi over 4. And the lower right is a rotation of pi over 2. Now, using the methods outlined in this lesson, we can evaluate the receiver operating characteristics for each of these situations, and it would look something like this. And these plots are shown for the situation when we get 5 independent realizations of the random vectors in each of these circumstances. Now, as expected, as the covariances become more different, the performance becomes better. The situation with a slight rotation has the worst receiver operating characteristic. The situation in green has the best. Well, in summary, numerical inversion of the characteristic function is one way to approach performance analysis for multivariate Gaussian hypothesis testing when the means are equal for the two hypotheses.